Hello everyone, in this video we're going to discuss trig identities and where they are useful and how to apply them. So first off, what is a trig identity? Alright, there's a difference between an identity and a conditional equation. Alright, so let's just take a look at the difference a little bit between that. Again, an identity versus a conditional equation. Alright, an identity is true no matter what number is inputted, assuming that it's defined, while a conditional equation, it may only be valid for some numbers or maybe not any numbers at all. So for instance, looking at this first bullet here, we know if we square out that binomial, we square the 2x to get 4x squared, we square 1 to get 1, and we get double the cross terms. 2x times 1 is 2x, double that we get 4x. So that's true no matter what x value we plug in. The second bullet here, that's a linear equation. We know how to solve that very well. We're only going to get one numerical solution, so that's only valid for one number. So the first one is an identity, the second one's a conditional equation. Some familiar properties that we know about, we can also think about as identities. So we know we can take the square root of a product and rewrite that as the product of the square roots. We know some properties about logarithms. Assuming those values are defined on the left and right hand sides, those are true for all of the numbers for which they're defined. Again, those are identities or facts. All right, now we're going to look at some trig identities that we know and talk about some other ones that we can derive. But before we get to that, what are trig identities useful for? All right, I've got three things listed here. All right, the main thing we're going to be looking at actually is the last bullet. We're mainly going to be looking at in this video using the trig identities to help us solve trig equations. Other applications we're going to see is finding the exact values of certain trig functions for certain angles like 15 degrees or 22.5, which is half of 45 degrees. We can express those values of those trig functions, say cosine or sine, in exact form, meaning we can write them down using familiar math symbols like square roots, using certain trig identities. All right. And again, this is a little bit historical, but it's good practice for getting used to using the identities. The only angles we know how to compute with so far are the main ones, about 30, 60, or 45 degrees, 0, 90, or other quadrantial angles. All right. Further, if you go on to calculus, or in particular, this happens a lot in calculus 2, for integrating powers of trig functions, there's need to rewrite expressions like cosine squared or sine squared or cosine to the third or sine to the third power in terms of lower powers of cosine or sine. That is possible with trig identities. All right, so there are some uses for them in various math classes and context. All right, what's some trig identities we know about or should be known to us? Right, the reciprocal identities, a definition for tangent and secant and cotangent and cosecant are given here. Tangent is equal to sine over cosine. It's an identity. Cotangent is the reciprocal of tangent. It's cosine over sine. Secant is defined to be 1 over cosine. Cosecant is defined to be 1 over secant. So we can think about those as identities as well. All right, the most important trig identity of them all is the Pythagorean identity for cosine and sine. All right, so it says cosine squared plus sine squared is equal to 1. That comes from the fact that every point on the unit circle is of the form cosine of theta, sine of theta, and comma sine of theta. All right, the unit circle has the equation x squared plus y squared equals 1 in terms of x and y. And if you substitute an x cosine of theta for x and sine of theta for y, you get the first identity written there. To derive the other two, you simply just divide the first identity by an appropriate value. So let's just do one of those for this recording. So we have cosine of theta squared plus sine of theta squared is equal to 1. All right, now what we'll do is we'll derive the second one. So what we're going to do is divide both sides by cosine of theta squared, and we have to distribute that division to each term on each side of the equation. And in doing that, what we're left with is, well, the first term here is 1. We got sine over cosine, and they're each squared, so we can think about that as tangent of theta, and then that being squared. All right, now remember, we write this with the shortcut notation where we put the little 2 on top of the tan part, but this really means tangent, the angle, or the value of tangent of theta, and then that quantity squared. And likewise here, we can think about 1 as 1 squared, so this would really be the same as 1 over cosine to the second power, which would be the same as secant of theta to the second power. So there, that derives the second identity listed here. All right, so there's really three different Pythagorean identities, right? There's one for cosine and sine, there's one involving tangent and secant, and there's one involving cotangent and cosecant, which we're not going to really discuss. All right, the first one is extremely important. All right, the other two can be derived from that first one. All right, now we're going to work our way up to solving some trig equations using identities. All right, but first off, let's just rewrite this by solving the Pythagorean identity separately for cosine squared and sine squared. So I'm just going to do that off to the side here. So we have our main identity, which says cosine of theta squared plus sine of theta squared is equal 1. If I want to solve it for, say, cosine squared, we're just going to simply subtract over the sine squared. Now we are going to subtract that on both sides, and that's going to give us that cosine of theta squared will be equal to 1 minus sine of theta squared. And if we were going to do it for sine, we would simply subtract over cosine squared from both sides to give us that sine squared is equal to 1 minus, fingers are hitting some keys there. That sine squared would equal 1 minus cosine of theta squared. Those are really useful. All right, they're simple, but it shows us we can exchange cosine squared for sine squared. Not exactly, but 1 minus sine squared. And likewise, we can exchange sine squared for 1 minus cosine squared where convenient. All right, now let's get to some examples. All right, so we're going to finish this video with several examples. The first two, I'm just going to do one of them for us there. All right, those ones are going to involve not really any trig identities, but we are going to use these last couple of effects that we derived for the last two types. So let's do the second example that I've got listed here. Again, we're trying to solve these equations exactly if possible, or if not, rounded to 4 decimal places. So actually, let's do the first example, and then we'll see about some of the rest. So this one, we've got it equal to 0. All right, we can't use any of these trig identities that we just derived because we don't have cosine squared or sine squared. But notice each of these terms, there's two terms, has a cosine factor. So we're going to use factoring here for this one. And we're just going to simply factor out cosine and see what we're left with. When we take out cosine from the first term, well, there's only just one cosine, so we're left with a factor of 1. When we remove the cosine from the second term there, we are left with 2 times sine of x. And that's going to equal 0. So from here, we're going to use the zero factor property. We're going to set each factor equals 0 to rewrite this as cosine of x is equal 0, and then separately 1 minus 2 times sine of x is equal to 0. Okay, so let's do a little bit of rearrangement here. I'm going to skip some of these steps. We'd add 2 sine x over and then divide by 2. So this, after a little bit of rearrangement here, this equation on the right side of my vertical bar would say sine of x would equal 1/2. All right, so we've got two possibilities. Cosine of x is 0 or sine of x is 1/2. Now we're supposed to solve these equations for all solutions in the interval from 0 to 2 pi. We're not writing down the general solution. We're just looking for a subset. All right, when is cosine 0? Cosine is 0 when x is pi over 2 or 3 pi over 2. So those are our two solutions there. All right, when is sine 1/2? Sine is going to be 1/2 when x is pi over 6 or 5 pi over 6. Okay, if you look at your unit circle, all right, we could use the inverse trig function to, maybe solve that in degree mode and then switch it back over to radian. There's two solutions, one in quadrant 1 and one in quadrant 2. So the first equation there has 4 solutions listed here in exact form. All right, let's look at another example. The second example, I think I'm going to skip on that's listed there. For that one, we'd still want to use factoring, but we want to subtract over 6x from both sides to then use factoring there. So let's look at the second equation, or the third equation that I've got listed here. All right, so we took care of number 1. We're going to skip number 2 there, third example, and then maybe we'll look at the fourth if we have time. So for this one, again, we're going to want to use some factoring for this problem. All right, so for that one, let's do that first move there by subtracting 1 from both sides to rewrite this as 2 times sine of t squared minus cosine of t minus 1 equals 0. All right, again, our goal is to isolate t, which we're going to do, but we can't do that directly from this problem. We're going to need to apply one of the trig identities we derived a moment ago and replace the sine squared to get it in terms of cosine, so we can either use factoring the quadratic formula. All right, so we're going to rewrite this as 2 and then times something minus the rest of it. We're just going to copy down. And we saw before we can replace sine squared by 1 minus cosine of t squared. All right, so now we're going to distribute the 2 through and rearrange terms. All right, so distributing the 2 through, we're going to get 2 minus 2 cosine of t squared minus cosine of t minus 1 equals 0. All right, now if we look at that for a moment, we can recognize that that is quadratic in cosine of t, meaning we see cosine of t to the first power, we also see cosine of t to the second power. I'm going to combine like terms. All right, so we've got 2 minus 1 that's going to give us 1, and then I want to move all the terms to the right side to make the coefficient in front of the squared term positive. So it would be 0 would equal, adding over the cosine squared, we would have 2 cosine of t squared. Adding over the cosine, we would have 1 cosine of t term, and then 2 minus 1 is 1. Subtracting 1 over, we'd then have minus 1. All right, so again, what we're thinking about here is this equation. If we let u equal cosine of t, then what this equation would really say would be that we'd have 2u squared. Sorry about that. Okay, apologize about that. Sometimes I hit something and it makes my screen scroll. So if we replace the u equal cosine of t, then this equation would say 2u squared plus u minus 1 is equal to 0. All right, now we can try to solve that either using factoring or using the quadratic formula. It turns out this example does factor, so we can use factoring to help us solve this. So this would be factored as 2u and u. If we had a product of smaller polynomials, we're going to have to certainly have 1 and 1, because 1 times 1 is negative 1. One of these would have to be positive, one would have to be negative. To make this work out correctly, we're going to have u plus 1 and 2u minus 1. So then we would, in this case, set each factor to 0. I'm going to skip a little bit of that work, so set u plus 1 equals 0. I guess I will write it, and then solve by subtracting 1, so we get negative 1. Then we would set 2u minus 1 equals 0, add 1 divided by 2. We would get u to be equal 1/2. All right, now backfilling here, undoing our substitution, we would have this. Cosine of t would equal 1/2, and then separately, cosine of t would equal negative 1. All right, and then we would have to solve that equation for t in the interval from 0 to 2 pi. All right, so when is cosine of t equal to positive 1/2? There's two angles, one in quadrant 1, which is pi over 3. All right, there's also one in quadrant 4, which is 5 pi over 3. All right, when is cosine of t equal to negative 1? All right, that only happens when t is equal pi. All right, so we can write these solutions down in exact form for this example. All right, and that's it for this problem. So let's look at the last one that we had. I'm just going to scroll back up to get that and bring it back down. Okay, so let's look at that example, that last example, and that'll be it for this video. All right, so this one problem was a little bit different. Here we had 2 cosine squared equals 3 sine of t. So very similar to the last one. We can't mix cosine and sine. We got to get it all into 1. So we're going to replace cosine squared by 1 minus sine of t squared. And then that will equal 3 times sine of t. Distributing the 2 through, we would have the following on the left-hand side. and then adding those terms to the other side. Again, it's nice when we keep the coefficient of the squared term positive, so we would have this resulting equivalent equation. All right, putting it in descending order, and we want to think about this as a quadratic type equation. It's a quadratic in the unknown sine of t for this problem. Now, again, we could try to solve this using factoring or the quadratic formula. Again, if you want to, you could, for this problem, let u equal sine of t like we did in the last example, and then this equation would say 2u squared plus 3u minus 2 would equal 0. And then we could solve that, again, either by factoring or the quadratic formula. Okay, so just to save time, I'm going to solve this one by factoring, but I'm going to factor it in terms of sine here and written in blue. All right, so if it's going to factor, it's going to be 2 times sine of t plus or minus a number, and then times sine of t plus or minus a number. Now, these things must multiply to 2, or multiply to negative 2, so we're going to have 2 and 1, all right, 1 positive, 1 negative. Again, this is the way it goes. You can verify it after you watch the video, and it turns out that this is going to be sine of t plus 2, and then 2 sine of t minus 1. All right, now set each factor equal to 0. Again, those things multiplied to 0 would mean one of these or both would have to be 0. One of these factors or both would have to be 0. We would have each factor set equal 0, each factor in the parentheses set equal 0. On the right side, about that. All right, brought it back down here. On the right side of my line, we would have sine of t equals negative 2. That has no solution, so we don't have to worry about this part at all. And if you do the inverse sine of negative 2, you'd see an error. Adding 1 and dividing by 2, we would get, in this case, sine of t would equal 1/2. All right. Now, when is sine equal to 1/2? There's 2 solutions to that. All right, just a coincidence that we came up with some of these repeated values for the purposes of this video. Other problems, we might need to use the quadratic formula to solve the resulting quadratic type equation we obtained. That's all for this video.